As kids, we've all played Pac-Man, navigating those mazes, eating dots, and dodging ghosts. These intricate pathways made the game exciting and challenging. But have you ever wondered how such mazes are created? First, let's ask the question, what's a maze? A maze is a complex network of paths or passages where the challenge is to find the correct route from the starting point to the finish. Mazes can have multiple dead ends and only one or a few ways to solve them, making them both puzzling and fun. Creating a maze isn't just about drawing lines and placing dots. It involves thoughtful design and clever algorithms. Designers carefully plan the maze layout to ensure it's challenging but not frustrating, while algorithms generate complex pathways and dead ends to keep players engaged and entertained. But what about a perfect maze? A perfect maze is a maze where every point is reachable and where there is only one single path from one point in the maze to any other point. In this video, we're going to explain how perfect mazes are created, explore some algorithms that enable us to draw mazes, and walk through the origin shift algorithm, which enables us to create mazes that keep changing while still being perfect mazes. Let's start with the depth-first search, or DFS maze, also known as the backtracking maze. To generate a maze using the depth-first search, or DFS algorithm, we start with a grid where every cell is surrounded by walls. We select a random starting cell, mark it as visited, and then look at its neighboring cells. From these neighbors, we randomly choose one that hasn't been visited yet, move to this cell, mark it as visited, and remove the wall between the current and chosen cell to create a passage. If we encounter a cell with all neighbors visited, we backtrack to the previous cell and continue the process. This exploration and backtracking create a complex network of passages. The maze is complete when every cell is visited and connected, forming a single continuous path between any 2 points without loops. Now we move to the hunt and kill algorithm. The hunt and kill algorithm starts with a grid full of walls and a randomly chosen starting cell marked as visited. From this starting cell, the algorithm explores its unvisited neighboring cells. If any unvisited neighbors are found, the algorithm moves to one of these cells, removes the wall between the current cell and the new cell, and marks the new cell as visited. This process of moving and removing walls continues as long as there are unvisited neighbors. When a cell becomes a dead end, meaning it has no unvisited neighbors, the algorithm hunts for any previously visited cell that still has unvisited neighbors. It then moves to this cell and continues the maze generation process. The algorithm repeats this hunt and kill cycle until all cells in the grid have been visited and interconnected, resulting in a complete maze. Now to the Prim's maze algorithm. Prim's algorithm for maze generation is a process that starts with a grid full of walls and selects an initial cell as the starting point. It marks this cell as part of the maze. The algorithm then maintains a list of walls adjacent to cells already in the maze. At each step, it randomly selects one wall from this list, and if that wall separates a cell inside the maze from one outside, it removes the wall, adds the new cell to the maze, and updates the list of walls to include those adjacent to the newly added cell. This process is repeated until all cells have been included in the maze. The result is a maze with interconnected pathways, ensuring a single connected component with no isolated sections. Now, let's move on to the origin shift algorithm. This algorithm, invented by a Minecraft player, helps us generate mazes that continuously change while ensuring they remain perfect. The origin shift algorithm starts with a perfect maze. Here, arrows represent open paths and lines represent walls. For example, imagine a maze where all cells are oriented to the right, except for the cells in the rightmost column, which are oriented downwards. In this example, our origin is the cell at the bottom right, which has no direction. We start with an origin cell and randomly select one of its neighboring cells. This new cell becomes the new origin. Then, we do the following steps. 1. Add an orientation or direction from the previous origin to the new origin. 2. Remove the wall between the previous origin and the new origin if it exists. Next, we update the new origin by 3. Deleting its previous orientation. 4. Adding a wall in the direction where there is no orientation. By repeating this process, we continuously shift the origin, creating a dynamic and ever-changing maze. Now let's take a look at the implementation of different algorithms. The source code is provided in the description below. Feel free to play with the parameters to see how they affect the algorithm's behavior and performance.